My name is David Roet and I work at the Flemish Environment Agency, mainly on topics related to air quality modeling, but I also like programming and playing around with data. In the Vacuums project, I mainly help with programming the ESPs and also with setting up and configuring data communication of the sensors. We will now show some of the main findings of the report for the low-cost nitrogen dioxide and ozone gas sensors. So, what is in the reports of the low-cost NO2 and ozone gas sensors? You will find a thorough comparison and statistical analysis of each sensor type and of the 5 individual sensors. We will address the following topics: validation and data coverage, how much sensor data is usable, calibration using orthogonal linear regression, when there was a linear relationship, or different multiple linear regression models in other cases. Comparison of uncalibrated and calibrated sensor data with reference measurements, the influence of ambient conditions like relative humidity, temperature, and other interference, and we will show the R-square mean bias between sampler uncertainty and relative expanded uncertainty. So, what are some of the main results? First of all, there is quite a big difference in the results of the NO2 and ozone low-cost gas sensors. For NO2, 3 out of 5 sensor types showed no linear relationship with the reference measurements, resulting in scatter plots with blobs and whales. Another problem was the occurrence of negative values. Here you see some results for NO2 sensors. On the x-axis, we have the NO2 concentration measured in the reference station. On the y-axis, the concentration measured by the sensor. The black line shows a perfect one-on-one agreement. On the left, you see that the alpha sense and the NVEA care clip show some kind of linear relationship, while on the right side, the CityTech and the Membrapore show no obvious linear relationship. You see shapes like blobs and whales. One of the ozone sensor types, the Aeroqual SM50, performed very well straight out of the box, with an R-square of over 0.9. Here you see the results for the Aeroqual SM50 ozone sensor. On the x-axis is the ozone concentration measured in the reference station. On the y-axis, the concentration measured by the sensor. We see that there's a very good correlation and an R-square of over 0.9. For this sensor, no calibration was necessary. Multiple linear regression models with the interferent pollutants NO2 for ozone sensors and ozone for NO2 sensors, and ambient conditions like relative humidity and temperature are able to improve the results, the R-square. But underestimation, a negative bias, and between sensor variations remain. Each sensor has its own fit, making generalizations complicated. Here you see the results for the Membrapore C1 and also C20 NO2 sensor. At the top are the results of the uncalibrated signal. At the bottom, the results after applying multiple linear regression model. Before calibration, we see that scatter plots show a typical non-linear relationship, here in the shape of whales, and the R-squared is very low, below 0.05. Also, the distribution of the sensor to reference measurement ratio has a very skewed distribution. After applying the second multiple linear regression model, we see that the scatter plots, the R-squared rises, but still has an underestimation. The distribution is no longer skewed, but the multiple linear regression models depend on good quality meteorological data, temperature, relative humidity, and good measurements of the interferent ozone and NO2 in order to work well. However, degradation over time and limited lifetime remain important issues. Here you see the results for the Membrapore C20 NO2 sensor. First, a time plot at the beginning of the field campaign in 2019. At the bottom, in the end of the field campaign in 2020. Let's take a closer look at the behavior over time for VQL4, sensor number 4. At the start, there was more or less a constant offset for the sensor. But at the end of the field campaign, there were a lot of spikes and strange behavior. There was a clear degradation of the sensor over time. So, what are some of the conclusions? There are big differences in out-of-the-box performances. Almost all NO2 sensors need a correction to become useful. For ozone sensors, the situation is better. The majority is usable. Calibration with a reference monitor is useful, but also is accounting for interfering gases. The extended multiple linear regression model, MLR2, is able to improve the raw measurements. Degradation over time remains an important issue for all of these sensors.